Today, we're tackling the 300-110 exam 8 crucial questions on wireless design. Let's jump right into question 1.
Sounds good. I'm ready.
So, first scenario, you've got a campus with 2 buildings, research and operations, and each has a Cisco 9800 80 WLC. For seamless Layer 2 and Layer 3 roaming, I'd immediately look at option C, setting operations as the anchor and tunneling traffic to it, since centralized traffic is cleaner, right?
Well, it's cleaner for guest networks, sure, but for internal clients, that's a massive trap. You actually want D, putting both WLFs in a single mobility group as equal peers.
Wait, really? Why not use an anchor?
Because anchoring creates this boss-employee dynamic. You want a relay race where equal runners pass the baton at full speed. Putting them in separate groups, like option B suggests, drops the baton entirely and breaks seamless roaming.
Ah, got it. Speaking of breaking connections, let's say you tweak the access points locally, like changing a flex profile name inside an assigned site tag on a 9800 WSLC. Modern controllers are pretty sleek, so option A, the AP updating automatically without downtime, makes total sense.
I wish. It's actually the AP entirely disconnects its DTLS session, the secure tunnel it uses to talk to the controller, and rejoins.
Hold on, it just drops. Why wouldn't Cisco do a seamless background update?
Because changing a site tag fundamentally alters the operational profile. It's like changing your phone's core language setting from English to Japanese. The system needs a full restart to apply it. So it's not a firmware upgrade or a backup failover, it's a structural reload.
Right, that makes sense. If AP's dropping is bad, what about clients? Say you have a VoWLAN SSID where dropped calls are immediately noticed. You need APs to suggest better roaming targets to voice clients without crashing unsupported devices. So option D, 802.11 error, fast transition, sounds perfect for speed.
11 error is fast, yeah, but doesn't actually suggest targets. It just speeds up the handshake. We really need C, which is 802.11v BSS Transition Management.
Ah, BSS Transition. So it acts like a GPS, calculating a faster route and suggesting it, but if you're driving an old car without GPS, you just safely ignore the suggestion and keep driving.
Exactly. 802.11k gives you a map of neighbors, and 11R is the fast lane, but only 11v actively tells the client where to go.
That's a great way to put it. What if the WLC fails over, though? Like migrating from older AreaOS controllers to a 9800 SSO pair. High availability is the goal, so option A, configuring the HA local and remote IPs, seems super logical.
That's a classic cognitive bias distractor. The real fix is C, configuring the wireless mobility MAC address.
Oh, I see the logic, because AreaOS peers identify the 9800 pair by its MC address. So if the primary box fails, the secondary needs to broadcast that exact same MC.
Yes, it's basically a permanent forwarding address when moving. Setting gateway commands or HA IPs won't fix the peer identity crisis when AreaOS comes knocking.
Zooming back to 9800 tags, let's look at what actually lives inside a site tag architecture. Since VLANs dictate local traffic, I'd argue option D, the VLAN profile.
I have to disagree there. It's actually C, the flex profile.
Wait, just the Flex profile?
Yeah, think of the site tag as a manila folder dictating how an AP behaves locally. The flex profile is the specific local switching document filed safely inside it, whereas options like QoS or NAT are policy and routing concepts, so they belong in policy tags.
Okay, so how do these WLCs broadcast to each other globally? Say you have 3 controllers in the same mobility group using multicast messaging. Option C, the management IP, is how they talk, right?
If they matched management IPs, you'd have an IP conflict that crashes the network. Management and service IPs must be strictly unique, so it's D, the multicast IP address.
That's a trap I almost fell into. So for multicast, it's like walkie-talkies. They all have unique names, but they must be tuned to the exact same frequency, the multicast IP, to hear the group broadcast.
Perfect analogy, yeah.
From WLC signals to client signals, let's look at optimized roaming. You've got it set at -72 dBm, but clients are dropping constantly. Option C says to enable BSS transition at the radio level and optimize roaming on the SSID.
Oh, you've got it backward. That's the reverse config trap. The answer is a BSS transition goes in the SSID, and optimized roaming sits at the radio level.
Oh, right. The radio level handles the raw signal. So it's the bouncer physically kicking weak signals out at -72 dBm. And the SSID is the VIP host politely using 11V to guide clients to a better table.
Exactly. Reversing those just fails.
Even with perfect signals, tunnels add overhead. Here's our last scenario. An anchored WLAN is serving video, but web traffic is crawling because of packet fragmentation. To fix it, option B says just increase the MTU on both controllers to fit larger packets.
If you try to force a bigger box through the same size pipe, it still breaks. You need, say, adjust the TCP MSS value below the fragmentation point.
Let me unpack that. MSS is maximum segment size. So instead of making the shipping box bigger, the MTU, we are shrinking the actual payload before we box it up.
Precisely. Matching MTU or setting do not fragment bits will just cause the router to drop packets entirely, so shrinking the TCP MSS solves the tunnel overhead gracefully.
Okay, we made it through. Now let's connect the dots.
We covered the core mechanics of wireless design today, starting with the equal peer logic of mobility group design and how tweaking site tags and flex profiles triggers AP reloads.
And we saw why 802.11 Win BSS transition is the best way to guide clients, and why locking in a mobility MC address for SSO keeps AreaOS migrations stable.
We also explored what really lives inside a site tag architecture, the walkie-talkie logic of mobility multicast messaging, and how to properly align your optimized roaming settings.
And finally, beating fragmentation by managing mobility tunnel MTU with TCP MSS adjustments. If 802.1 of V acts like a GPS for clients, how will AI eventually automate the entire roaming process?